What is the Collatz conjecture, 3n+1 problem? Imagine starting with any positive whole number and following a simple set of rules. No matter which number you pick, you might wonder what will happen next. Will it grow endlessly or settle down somewhere? This question has puzzled mathematicians for a long time. It involves a process that is easy to understand but very hard to prove. Here is how it works. Take any positive integer. If it is even, divide it by 2. If it is odd, multiply it by 3 and then add 1. Then repeat the same steps with the new number you get. This creates a sequence of numbers. Some sequences quickly drop down to 1, while others seem to bounce around before reaching 1. Once the sequence hits 1, it goes into a loop of 4, 2, and 1 forever. For example, start with 10. 10 is even, so divide by 2 and get 5. 5 is odd, so multiply by 3 and add 1 to get 16. 16 is even, so divide by 2 repeatedly until you reach 1. The sequence looks like this: 10, 5, 16, 8, 4, 2, 1. This pattern is called a hailstone sequence because the numbers go up and down like hailstones in a storm. The big mystery is whether this process always ends at 1, no matter what positive number you start with. Mathematicians have tested it with very large numbers, up to around 1 quintillion, without finding a counterexample. But no one has been able to prove that it works for every positive integer. It is a puzzle that connects simple arithmetic operations with unpredictable patterns. From the point of view of basic number concepts, the conjecture makes us think about how sequences behave when we apply simple rules repeatedly. It shows that even basic operations like dividing by 2 or multiplying by 3 and adding 1 can create complex behaviors. It also highlights how some questions about integers are surprisingly difficult to answer, even if they seem straightforward. If we try the same process with negative numbers, the pattern changes and often leads to different loops or endless growth. So, the behavior is different across the whole set of integers. This makes the problem even more intriguing. People have created computer programs to test the conjecture and visualize the sequences. These experiments help us see the patterns and understand how numbers behave under these rules. The Collatz conjecture remains an open challenge in mathematics, inspiring many to look for a proof or a counterexample. It reminds us that even simple rules can hide deep mysteries within the world of numbers.